to yourself. Surely this is a risky lemma in the discussion. I mean, and the fact that it was mentioned that actually the core of that is that the regular functions are indeed functions. They are separated by points. So the injection from A to the function space is indeed an injection. So this exactly means that the intersection of all maximal ideals is 0. Which, maybe you know, is the same as the intersection of all prime ideals. Because the intersection, this is a general fact, the intersection of all prime ideals is exactly the ideal of nilpotent element. And here we assume this is trivial. And in particular, it follows that the intersection of all prime ideals is the same as the intersection of all maximal ideals. And actually for this, we don't need to assume that there are no nilpotents, because you can always divide those up and get this. And this implies, maybe this version, whatever version, or this is actually equivalent, whatever version of Nutschensatz you happen to know. Take this to next. It should be very easy. Okay. Next thing I want to discuss is products. Of course, I want to discuss algebraic groups. And algebraic groups, affine algebraic groups are just group objects in that category. Maybe I'll write this thing down. But it doesn't make sense yet. Affine algebraic group are group objects in the category of affine space, affine varieties.
So also from categorical viewpoint, product with the list topology is a product in the category.
Let me explain what I mean by this. Once your category has products, the term group object is well defined, and this is some guy G, such that you have multiplication maps and inverse map satisfying various axioms. And only this makes sense if we have product in the category. So this is what I want to discuss now. Products. And this is the category of affine algebras, or in fact the category of algebras as products. These are tensor products. And the full subcategory of affine algebras is the same product. Tensor product of affine algebras is affine as well. This is an exercise of affine algebra has products. So the construction known as tensor products of algebras. So this, let me sketch this. A tensor B is something that contains A, it contains B, and whenever you have something C here, blah 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 blah. You know the diagram. And just dualizing, there are products from affine varieties, the dual category. This category has products. Nothing to prove, just one observation. Now, but I better relate this. I should have said co-product, I said.
Two are categories.
I should have used the co-products in the... Yeah, sorry. So, or sums. Somehow I don't want to use sums for this kind of product. Okay. Sorry for that. And now, but I want, of course, to relate these two spaces. I will leave you to check the following. Check that the spectrum of A tensor B, this is an easy spectrum, is isomorphic naturally. You should define this isomorphism as well, of course, with the product space. As sets. This isomorphism is actually a homeomorphism this is going to check for the Hausdorff topology. So we defined Hausdorff topology on varieties, and these are and these isomorphisms that you have here actually respect this structure. So if you consider those as topological spaces, this topological space, this topological space, this topological space, and you take the product here, product topology, this will be a homeomorphism. This may come with no surprise, but I guess I will not surprise you as well when I consider the following fact, which you are familiar with, but it is different for the Zariski topology. This is not the case for the Zariski topology. So if you take C2, obviously these are all closed sets, which kind of fit with the product topology, but also this one is a closed set, which you don't see for the product topologies. Exercise, another exercise. But for both topologies, if you take the projections X or Y are open maps. I'm sure that if any of you sees those things for the first time, this is way too fast, and I'm leaving for you too many exercises. But if you have already seen these, those exercises I'm leaving are really things that are easy to do. So just to refresh your memory. Okay. Now I want to present the result here. For every morphism of a fine variety. There exists U in the image.
In the exercise, X times Y topology is...
Either. So for both topologies.
but for Zariski, is it
Well, okay, so I should add this, I will not write it down. Whenever I consider x times y as an affine variety, I consider it with the risky product topology, which is the risky topology of such a thing. Sorry. So I will write many times x times y, and whenever the risky topology is considered, this will not be the risky, the product topology of the risky topologies. So here I wrote two exercises. One, consider x, y, and x times y with the product topology of the Hausdorff topologies, and x with the Hausdorff topology, and this will be an open map. And the other is just about the risk topologies. Sorry. For isomorphism, there exists U, which is open inside the closure of the image. Now we have all the ingredients to give a quick proof of that. So of course, without loss of generality, I may assume that Y is the closure. Or in language that that phi is a dominant morphism. And that phi Y injects into Cx. Now, I'm doing something very similar. It is very similar to how these steps to how I prove the lemma related, or this risky lemma, I guess. So just you take OX, and this is finally generated over OY as an algebra, not as a model. This I don't know. I don't know if this is finite, but somehow I want to arrive at this situation. So take OY, and I can find element. I did it before with X and Y. Now X and Y are kind of points in the spaces, so I'll use terms U and V. Well, U is U1 to UN, algebraically independent. Over OY, V, another bunch, VM, algebraic over the rest, OY, U. So again, I know finite generation, so I know that I can just find some finitely many variables here, not variables, element of OX, that will generate as an algebra. Take the U's to be some maximal algebraically independent set in the variables, and the V's to be the rest.
Algebraically independent means that we can satisfy
no polynomials. No polynomials over OY, so no polynomials over I don't know, any localization of OY. Same as before. I'll find F inside OY extended with the U's such that the rest is a finite module over the localization by F. I just need to make clear that it's not OX which will be finite generated module over it, because I need to add 1 over F to it, such that OX 1 over F is an integral extension of OY. I'll repeat. I will not write it down, but I'll repeat what I'm saying. Think of the algebraic number V1. This is algebraic over
no one over F on the left.
yes, there is, must be. I mean, otherwise, it's not an extension. I had to add it. So, but take V1. This is an element of OX. And it satisfies, I know, some polynomial over that one. And if I divide by some coefficient from this guy. So it satisfies some polynomial from this guy, polynomial in some other variable, t. I'm not writing those things. And this polynomial may not be monic, but I can divide by something to make it monic. And this something, okay. And also I will do it for V2 and V3, etc., etc., etc. I wanted to satisfy monic polynomials. For each one, I have to divide by something, collect those things, multiply them up, and divide by the product. That will be good enough for you. This is F. So F is an element here, which I think of now as, I was thinking for a minute as a constant when considering polynomials in another variable on that, over that. And the ring generated by these integral elements now will be a finite model, because a high enough power of V1 will be sum of a convex combination, linear combination of lower powers. So the algebra generated is actually the finite generated algebra by these is actually finite generated model. Those lower powers will be the generators. And in order to do this, again, I had to introduce 1 over f into the business. And now set xf to be f minus 1 of k minus 0. This is a standard notation that we're using inside x. If you think of f as a function on x, this is the non-zero. So xf sits inside x. This is an open set.
F minus 1, k minus f of what? What is k?
K minus 0, I mean the non-zero point in the field. F is a function, it's a regular function. So I want to think about it as a function to the field. So F is an element where I choose it as an element here, but everything here is inside X, right? It's inside OX. F is an element of OX, it's a regular function on X. Take the principal open set defines. It's what you call. This is a standard notation point, X star F. And this is the spectrum of, this is naturally identified with the spectrum of O X 1 over. Again, this is the standard process called localization. And there is a natural map here to O Y. I mean, just the inclusion of the corresponding algebra into here. Spec. Ignore the specs and reverse the error. This is just the inclusion. O Y use 1 over f. And this is onto because it is finite. But what is that one? This sits inside OY. It's just a F principal set in OYU. Spec.
The 1 over f
ignore the specs decorations and reverse the error. This algebra embeds in that algebra, embeds in that algebra. And I wrote specs and invented errors. Okay? But I'm getting some understanding on the level of specs. I know that this is finite. So this is onto. And I know that this is open in X. And similarly, I know that I know the relation between these two. Actually, what is that? What is OY? The U's are independent, right? So actually this guy here is OY, tensor product with K, with the variables U. I hope you can see. With K, the variables U. And this is, well, I didn't introduce the notation, the very standard notation here. Miel introduced it last time, but I hope you're all very familiar with this. The spectrum of this is what we call the finite space. Here you have n many U's. Right? So the spectrum of U's defines n space, and this is just y times n. Again, n is the number of U's. And this inside is just the pre-image of the non-zero element under F. This is open. And now I can project on one of the factors. Let's project this one to 1. This is open map. And the image of XF was an open guy. Here, it was mapped onto that set. And the image in here would be an open set. Let's U be the image of XF. Here. So this is on. This is open. Because the map, the projection map here, is an open map. And this was open inside here. Which is the pre-image of an open set. Okay, so again, if any of you sees this kind of things for the first time, it's a bit confusing, but it's not very deep. And this U is an open set. Of course, this is contained in the image of X.
This theorem should answer this set U is dense.
Well, X is dense in Y. I was assuming that already X is dense in Y. Sorry?
In the theorem, you didn't formulate it this way. You didn't write that U should be dense.
Okay. I could have get more, but I did prove the theorem.
It could be empty, yes. You could be.
Oh, not empty. I got I mean, the fact that it is dense, I think, follows from this.
So an empty set is lower than
Okay.
dense.
Not empty. Yeah, you can get dense. Somehow I didn't want to add one more adjective for the reducibility into the proof. And to avoid this, I didn't discuss density. It doesn't matter so much, I think. So this is actually a very important term, very deep, and related to logic, as people here know very, very well. So maybe I will introduce the term, the extension of this called Chevalier-Tarski theorem. But just maybe before, let me add more definition to the business, just to make some induction. Process. A topological space is called Noetherian. If every collection of closed sets has a minimum. Not necessarily a minimal element, but a minimum. Hilbert basis theorem. Which I hope we're all familiar with, says that an affine algebra is Noetherian as an algebra, which means every collection of ideals as a maximum. By duality, you get the following theorem. So just maybe, the Hilbert-based theorem says that if it's an induction step, it says that if A is Noetherian, then polynomials over A, AX is Noetherian, but then by induction I can add every finitely many variables, polynomials in finitely many variables over an affine algebra. Over an Noetherian algebra is Noetherian, start with a field. The image of Noetherian algebra is Noetherian algebra. This is very easy, and you get that every finally generated K algebra is Noetherian. And if you dualize it into spaces for the Zariski topology, and maybe check one or two things, because I was very brief, you get that the Zariski topology on an affine variety is Noetherian. Oh, I should change this to an exercise. I will not change it now. And this, of course, it doesn't follow for the Hausdorff topology. Hausdorff topological space is never Noetherian, unless it is finite. This is maybe, you can take this as another exercise. But the Zariski topology, well, in particular, it is very much non-Hausdorff, of course. The Zariski topology, and now I want to state then the theorem by Chevalet, or proven by Tarski, sometimes called the elimination of quantifiers over algebraic closed fields, but in geometric language, we say the image of a morphism is constructible. We know what a constructible set is, topological space is. And of course, it is also age constructible, just because topology is stronger. In fact, it's very easy to get from it, maybe this, not precisely, to, in fact,
Okay, so
exercise, maybe, in fact, every morphism. I already use this adjective for macro-topological spaces, then why not use it? Every morphism is constructible. This means that the image of every constructible set is constructible. It is very easy to use this for that. And actually, it is very easy to deduce this from that.
Could you repeat what you mean by constructible morphism?
Constructible continuous map. So a constructible was an adjective describing a continuous map between topological spaces, and it means that the image of a constructible set is constructible.
I see.
Okay? And this is, so this, I don't use it as an adjective for a morphism because people don't, because this is just, it's satisfied by all morphisms. So there are, I mean, of course, we have many adjectives for morphisms. Finite was one, dominant was one, others. Constructible is rarely used because it is standard. Though, actually, it is interesting notion if you discuss non-closed fields. And there are very interesting theorems. I hope I will have the time to discuss some of them, but of course not big proofs now. So the scope for our discussion here at that moment is over algebraic closed fields. Okay, I want to give a proof of that theorem. So assume I'm having a morphism x to y. Fix maybe assuming it is not constructible, but the image of x is not constructible, then I want to use the Noetherian hypothesis to find a minimal representative of such. So vary over all the subvarieties of x and take the minimal guy with that property. Fix a minimal element or minimum element. Well, the minimal is not the minimal. X0 in the collection all the x prime in x, x prime is closed, so the subvariety, and phi x prime not constructed. So I'm surprised that no one told me that in definition I will write non-empty here, and by this assumption, this is a non-empty collection, and by Noetherianity I can pick a minimal element and let's denote it x0. So now I will use this theorem to get a contradiction. So let's find U inside the image of x0, which is open in the closure. Notice that U is locally closed, particularly it is constructible. then now phi x0, of course, is mostly U. I mean, I'm saying mostly because I'm familiar with this topology. I know that U is almost everything, but of course there is some rest. Let me describe the rest as non-empty. The rest will be the image of phi inverse of phi x minus U. The image of the complement, x minus phi inverse U. And check that this is closed. Thank you. Check that this is closed, subvariety of x0. So it's a smaller element in this collection. So the image here is constructible. And this is constructible. And also this is constructible because this is locally closed, and the union is constructible. Is constructible. A contradiction. Okay, so we put this Chevrolet-Tarski quantifier elimination theorem, which again, in geometric language means that morphisms are very, very nice topologically. The image of a constructible set is always constructible, or at least the image of a closed set is constructible. This is what we proved, but it is not very hard to promote this to that. Now I want to give some, to go to algebraic groups briefly. And to give some corollaries, I guess that I should start by giving some examples, etc., etc., etc. But we are at the very end of this hour, and I want to somehow to get as much out of this theorem that we proved to the theory of algebraic groups. So we have already the definition. And let me give some very small propositions to be used in later lectures. If H in G, G algebraic now is a synonymous from now on to an affine algebraic group. H in G, any subject. Then, first of all, and this is a very general thing, a bar, the risk closure, is a group, is an algebraic group. I think at this point I will leave this as an exercise. Basically what you need to show is that it is closed under multiplication and inverses. And those properties are, even though maybe we are used to for topological groups, so the product topology is a topology on G times G, this is not really needed in proving this. So I'll leave it to you. And for us, more important, if H is constructible, then H is closed. So let me prove two now. If H is constructible, then we know that there exists U in H such that U is open or not empty. Open in H bar. Here I didn't use the Chevalier task. I think this is general thing about constructible sets in topology that I mentioned. Whenever a constructible set is a union of locally closed things, and there is some canonical decomposition. There's a biggest guy. So this was part of an exercise that I gave, and actually I think Miel will do it today, right? So now I'm just taking it for granted, and check. So I'm leaving some details. Just that H also is open in H bar. Okay, I'm writing this at this form, but it's actually very easy. H contains U. It contains also all translates of U by all elements of H. H equals the union of all translates of U by all elements of H, and this is just a union of open sets. So H is a union of open set. It is open itself, but an open subgroup inside a group is always also closed, right? Because the complement is the union of all concepts, which are open as well. Then H is closed in H bar. Again, this is something that you are probably very used to from topological groups. But it is also the case for algebraic groups. You don't use the product structure on G times G, or H bar times H bar. We're considering this. Just the fact that basically that the H acts on itself by homomorphisms. I use that fact here and here as well. Only that fact. And suppose in H bar, that is H is H bar. And it is closed. Yes. I didn't need some time. In any case. Okay. And let me write another corollary. For every algebraic homomorphism, what is that? G to G prime. This is a shorthand notation. G and G prime are algebraic groups, and this is a morphism of algebraic varieties, which is also a homomorphism of groups. Okay, I'm not writing all these words. But I do get that phi G is closed in G prime. This is very, very special thing. Algebraic homomorphisms are always closed. And we get this for free, and I guess what I wanted to do now, well, I guess I wanted to give some example, etc., 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 but somehow I am postponing this more basic discussion. What I will do next time, I need to end this class now, is to consider a generalization of this, not for just homomorphism between groups, but also for actions. So I don't do it now very briefly. I could, because when I am considering action, I need to extend my point of view and think not only of affine algebraic varieties, but on general algebraic varieties. And this is because many times coset spaces, G mod H, turn not to be affine. So we need some extended point of view. So next time we will do general varieties, coset spaces, the beautiful theorem about tameness of actions of algebraic groups and algebraic variety, and then I hope already next time we will start doing some ergodic theorem, such varieties. So in particular we will study measures on algebraic varieties. Okay, so sorry for that this was so basic. I hope it will get better.